Before we start looking at what complex numbers have to do with polynomial functions, let's remember that sometimes we can have complex solutions to a quadratic equation. So the instructions for this problem ask us to solve it using the quadratic formula. Remember what that is. It's x equals the opposite of b plus or minus the square root of b squared minus 4ac all over 2a. And so x will equal 2 plus or minus the square root of 2 squared minus 4 times 4 times 9, all over 2 times 4. So we simplify, and we get 2 plus or minus the square root of 4 minus 144 over 8. Continuing to simplify, we have 2 plus or minus I times the square root of 140 over 8. Let me pause for a second. From here, you would realize that you're going to be taking the square root of a negative number. So you factor the I out, and now you've got a positive number inside the radical. This positive number, well, I look at the last two digits and notice that that's divisible by 4, so I know that 140 is divisible by 4. So we pull out our handy-dandy calculator and we see what 140 divided by 4 is, and it's 35. And 35 does not have any additional perfect square factors inside of it, so I know that I'm going to factor this, or I'm going to rewrite this as 2 plus or minus, let me go step by step, I times the square root of 4 times the square root of 35 all over 8. This is 2 plus or minus 2i radical 35 over 8. And finally, since 2, 2, and 8 are all divisible by 2, I can finally reduce this to 1 plus I radical 35 over 4. So in chapter 2, we talked about how when we have a polynomial function, the degree of that polynomial function is the number of possible real zeros. And what we realize here is that the degree of this polynomial is the same as the number of solutions that this has, whether real or complex. And so this leads us to another property, what we call the fundamental theorem of algebra. And the main thing that we're trying to get across here is that a polynomial function of degree n has exactly n zeros, or n solutions. And we include repeated zeros, and that is in the complex number system. And again, remember that in the previous lesson we talked about how real numbers are complex numbers. So what we've figured out here, or what we've established here, is the degree is the number of solutions that will exist. So when we take that and we extend it to talking about the factorization of a polynomial, we see that we can express a polynomial as the product of a bunch of linear factors, x minus the zeros of a polynomial function. When I go to solve this equation, I realize that it's a quadratic. However, I don't have an x term, so probably the easiest way to solve this equation is to get the x squared by itself by subtracting 20 from both sides. So when I do, I'll have x squared equals negative 25. And when I go to take the square root of both sides, I get that x equals positive or negative the square root of negative 25. But of course, you know that the square root of 25 is 5. You know that I can bring an I out of this radical in order to take care of this negative. And so our answer would be positive or negative 5i. And so if I take this into consideration with these examples that we just did, we can realize that this equation can be expressed in a factored form. It could be expressed as x plus 5i times x minus 5i. That's the same thing as x squared plus 25. We're given the zeros of a polynomial function, and we're asked to write the polynomial function for it. And finally, one thing that's helpful for us to keep in mind is that if a complex number is a solution to a polynomial function, its conjugate will also be a solution. So, for example, here, we know that -3 is a solution, that 1 is a solution with multiplicity 2, and we know that 4i is a solution. So realize that this 4i, that is equivalent to 0 plus 4i. And if 0 plus 4i is a 0, then -4i is also a 0. Now, they didn't give that to us, but we are expected to figure that out. And so we can now write this as x minus -3 times x minus 1 squared times x minus 4i times x minus -4i. And so what we're expected to do is to multiply all of this out and get one polynomial function whose zeros are these. So here we go. I can rewrite this as x plus 3. I can rewrite this as x plus 4i. And if you remember from Algebra 2, maybe Algebra 1, that when you multiply x minus 4i times x plus 4i, this becomes a difference of squares. So let's do that. This will become x squared minus 16i squared. And I'm going to be multiplying that times x minus 1 squared times x plus 3. What's next? You might want to multiply this out, keeping in mind, please, for the love of all that's holy, you don't just square this and call it a day. You must FOIL it out. You must realize that this is x minus 1 times x minus 1. And so when we multiply that out, we've got x squared minus x, that's minus 2x, plus 1. And now that I'm going to multiply times x plus 3 and times, let's go ahead and clean this up. We know that I squared is -1. We know that -1 times -16 will be x squared plus 16. And now from here, we've got some more multiplying to do. And I thought I had provided you with a good bit of space, but I may have to edit how much space I'm giving you to make sure you have space when you take these notes. Okay, so we are continuing to multiply stuff out. Myself personally, I might multiply these two together next because it doesn't matter the order in which you multiply these things. Remember that the commutative property of multiplication says that order doesn't matter when you're multiplying. All right, so I'm going to multiply the x plus 3 times x squared plus 16 next. And that's going to give me x to the third plus 16x plus 3x squared plus 48. And now that finally, actually let's write it in standard form, shall we? x to the third plus 3x squared plus 16x plus 48. We're going to multiply it by this one that we still have left, x squared minus 2x plus 1. So what you need to realize now that we can't just call it FOIL is what you're doing is multiplying everything in this parenthesis times everything in this parenthesis. Here we go. X to the third times x squared, that's x to the fifth, minus 2x to the fourth, plus x to the third. Keep going. I've got now this one times everything, so plus 3x to the fourth, minus 6x to the third, plus 3x squared. Now I'm multiplying this times everything. So plus 16x to the third, minus 32x squared, plus 16x. Finally, multiplying 48 times everything, plus 48x squared, minus 96x, plus 48. Whew. And now I combine like terms. So that's going to equal x to the fifth. Let's combine our x to the fourth terms. There's this one and this one, and that's it. So negative 2x to the fourth plus 3x to the fourth is plus 1x to the fourth. Combine our x to the thirds. I've got this one, and this one. Okay, so 1x to the third minus 6x to the third, that's negative 5x to the third, plus 16x to the third is 11x to the third. Continuing, I'm going to combine these x squared terms, and I have 3x squared minus 32x squared is negative 29x squared. And when I combine negative 29x squared with this positive 48, I get plus 19x squared. Finally, I have this 16x and this negative 96x. And when I put them together, I have negative 80x plus 48. And this polynomial is the answer. And as you can already guess, you're not going to be assigned a whole lot of these kinds of problems. But it is something that we here in advanced topics do need to cover. Let's look at 6b. So once again, I have this complex number, so I know that its conjugate will also be a 0, so that's 1 minus I. So I know I've got x minus 2 radical 3 times x plus 2 radical 3 times x minus 1 plus I times x minus 1 minus I. These, once again, take your shortcuts where you can get them. If you've got two binomials that you're multiplying together and you know that multiplying them together will give you a difference of squares, use that. So when I multiply these two things together, I will have x squared minus the quantity 2 radical 3 squared. Well, remember how to do this. You're going to multiply the 2 times 2, that's 4. Square root of 3 times square root of 3 is 3. And 4 times 3 is 12. So I have x squared minus 12 times x minus 1 plus I times x minus 1 minus I. Now, I don't know about you, but the prospect of foiling this out just makes me really want to cry. I mean, come on. But think about what it means for 1 plus I and 1 minus I to be zeros of a polynomial. Let's do this off to the side. It means that someone, somewhere, solved an equation and got that x equals 1 plus or minus I as their solution. So let's try to figure out what that equation might be. So if I subtract 1 from both sides and I get x minus 1 equals positive or negative I could take this equation and square it and just have negative 1 over here so that I'm not dealing with that dreadful I. So I'm going to take this whole thing and square both sides. So I have negative 1 here equal to, now remember, you've got to FOIL this out. So this would be x squared minus 2x plus 1 equals negative 1. So this quadratic in standard form would become x squared minus 2x plus 2 equals 0. And now, oh look, this is equivalent to what I would find out if I FOILed out this nasty, dreadful, awful thing. So let's just put that in its place. X squared minus 2x plus 2. And now that's a whole lot easier to deal with. So just like we did in the last example, we need to multiply this x squared by everything in the second parenthesis and then multiply the negative 12 by everything in the second parenthesis. So here we go. X to the fourth minus 2x to the third plus 2x squared. And now taking the negative 12 times x squared. I have minus 12x squared plus 24x and then minus 24. And when I finally combine my like terms, I've got x to the fourth minus 2x to the third. These are like terms, and when I combine them, I get negative 10x squared, and then plus 24x minus 24.